Hello, I'm James Green of Uber Solar, and welcome to this talk, which is on what affects solar performance. And it covers exciting areas like the weather and solar irradiation. And hopefully at the end of it, you will have a better understanding of how solar water heating systems work in conjunction with all of the factors which affect the performance. I'm going to use a number of slides to help try and illustrate this. And the first thing which we're going to use as an example is one of our 36 tube systems, which at 20 megajoules has an output of around 0.33 of a kilowatt hour per tube per day. So in this case, it's around 12 kilowatt hours. And we're going to refer to this example on a number of occasions as we go through. Now, solar performance, not surprisingly, depends on the weather. And I'm not as good as the weather forecast people who just put their hands out everywhere. So I'm going to use a mouse. But if you have rain all day, there will be some solar irradiation, but it basically falls pretty low. And at the other end of the spectrum, if it's very sunny, perfect clear days, it's going to be over 100% performance. Sun cloud will be 80 to 100. So what I call fairly self-explanatory and to be expected. Now, the extraordinary thing to me about energy from solar is the amount of energy which is hitting the Earth. 1 square meter, and just think about that a second, 1 square meter is not very big, will have around 5.5 kilowatt hours of energy every day from the sun on a typical average day, more on very sunny days. And if you could capture that, it would heat 100 liters from cold to 60 degrees, which it's an enormous amount of energy in a very small area. Just imagine if we could capture all of the energy in all of the area. So it comes down to looking at understanding solar irradiation. And what we're looking at here is a map of South Africa and with lots of pretty colors. And it's just done by a company called Solaris, who you can find on the internet. And if we look at Johannesburg and Pretoria and Gauteng, basically, we're just over 2,000 kilowatts of energy per square meter per annum. And we then have to make the whole thing more complicated. I don't know why people do this, but it's just the way that it works. So there's around 2,008 kilowatts hours per annum per square meter. If we divide that by 365, we come back to that figure I was just showing you of 5.5 kilowatt hours. And if we then do something, we turn the kilowatt into megajoules. Why? It's just because they do other calculations based on megajoules. And you multiply that by 3.6, and it gives you the megajoules per square meter. And in Johannesburg, that is 5.5 kilowatts times 3.6 equals 19.8. I know. Frustrating. But then if we look at the seasonal and solar irradiation in South Africa, it will begin to make sense. Here is Johannesburg, and in the middle of summer, we have a solar irradiation of around 24. In the middle of winter, when I'm making this recording now, it's around 14. And then it goes up and down. And basically what one's doing is you're taking those formulas and working them backwards. So here's Johannesburg at 20, being the average throughout the year. If we throw Cape Town in just as illustration, it's quite interesting. And Cape Town has that 29 figure, very high in summer, and quite low in winter at 9. It's about the same as London, actually. And if you look at Durban, just in contrast, it's not as good, mainly because of the coastal cloud, although the air temperatures are higher. So what does that mean when we come back to our 36 tube system? We know that at 20 megajoules, it's around 0.33 of a kilowatt hour. And if we look at that in terms of the maths, the deemed output is around 11.88, which is 100% efficient in the electricity replacement. And it's going to give us around 428 liters of washing temperature at 40 degrees at the tap. And that means we could have 28 minutes of solid non-stop showering in one go. But let's just look at it in winter. because the solar irradiation has fallen from 20 to 14. And what that means is that there's going to be less hot water in the winter months. And the 14 megajoules comes because the days are shorter. You know, the sun gets up later in the morning and goes to bed earlier than it does in summer. And it also moves. So it's 290 liters down from 414, but in summer, when it bounces up again, you're getting 497 rather than 219, or 290 and 414. So that illustrates basically what's happening. So we can look at it up and down. Now there's another big factor which comes into play, and that is cold water temperatures. And cold water temperatures fluctuate quite significantly between the summer and winter. In the summer, they're 20 to 21, and in the winter, they are down as low as 11. So we have an average of 16. Now, just forget solar completely for a second, and let's just look at your electricity bill, and you think, God, my electricity bill's so high in the middle of winter, and it is. Because if you look at the amount of electricity that you've got to use to heat the water to the same thermostat temperature every day of the year, in the summer, it's going to be about 25 to 30% less than it is in the winter. Winter is really quite high and summer is quite a lot lower, and you can see in the blue line the temperature. So you're getting more energy being used to heat the water for the same result, just because of the water temperature. Now, if we bring solar back into the equation, we know that we're going to have more performance in the summer and less in the winter. And in looking at a 150 litre 24 tube system, which is the same as basically a 200 litre system with the same number of tubes, just that we size it accordingly, the hot water temperature in the geyser is going to hit about 73, 74 with no electrical backup. Fantastic. But come the winter, 45, 46, only a little bit warmer than showering temperature. And what that means, very simply, is you're going to have electrical backup, because everything's against the solar system. It's not that it's not performing, it's just that the days are shorter, the water's colder, the air temperature's colder, everything. And the blue sort of pyramid is showing the amount of electricity that's got to be put in to take it up to the thermostat temperature. And we then have the evil of heat loss, of which I discussed in another video, where because the nights are cold, the geyser just loses heat up into the air. So solar performance is determined by a number of factors. If we start here, an area we haven't discussed, orientation. Is the solar system facing due north? If it's facing due west, it's going to be nearly as good, but not quite as good. If it's facing anything more than 45 degrees east of north, the performance is going to drop off rapidly. Inclination, the ideal inclination is latitude plus 10 degrees. That means about 37 degrees, but it doesn't make as much difference to the orientation, so you can have a much lower pitch. But shade is a big factor. So the actual positioning of the solar system is important. You then got the deemed performance, the output of the system itself. How good is it at 20 megajoules? Because that's our sort of baseline to work to. We then have the weather, which we know that you can go from rubbish on rainy days to fantastic on very sunny days. You've got the location, depending on where it is. Johannesburg, Pretoria, Cape Town, Durban. You're looking at the irradiation. You're then looking at the seasons, the amount of irradiation for that time of year. And you're looking at the water temperature. And then really, to throw in another curveball, you're looking at air temperature. And of course, you're going to lose more energy in the winter, when the air temperature at night could be down as low as freezing, whilst in the summer it's going to probably be somewhere between 15 and 20 degrees. So it works exactly the same with solar PV, but it's slightly different. Here's an example of a solar PV system on a factory we've done. And if one's looking at the projected power output of this particular system, the purpose of the slide is to illustrate that you can see the amount of energy is much less in the middle of winter than it is in summer. So the next steps are for you to please get in touch with us, call us on chat, visit the website. There's a lot of information there. Email us if you want more information, and of course be informed by watching more videos. And with that, I'd like to say thank you very much for listening, and we look forward to telling you other things about solar, and good evening and thank you very much.